Previously, an organization reported that teenagers spend 10.5 hours per week on average on the phone. The organization thinks that currently the mean is higher. 22 randomly chosen teenagers were asked how many hours per week they spend on the phone with the following results in hours. Perform a hypothesis test using an 8% level of significance. Okay, so let's start with our null and alternative hypotheses. We are told that we're dealing with the average, with the mean. So we are dealing with a hypothesis on the population mean. Okay. The first statement here, that the organization reported that teenagers spent 10.5 hours per week on average on the phone. Okay. So that means that the population mean, and what was it, 10.5 hours? So the organization said previously the average was 10.5 hours, okay? Not greater than 10.5, not less than, not at least, not no more than, exactly 10.5 hours, okay? The organization thinks that currently the mean is higher. So currently the mean is higher than 10.5. So that means the mean would be bigger than 10.5. So these are our two inequalities. This first one has an equals in it, so that's our null hypothesis. This other one has a greater than in it, so that's our alternative hypothesis. So let's put those in. So null hypothesis is that the mean is 10.5, but the alternative hypothesis is that the mean would be less than 10.5. Oh, I'm sorry, mean is higher than 10.5. So greater because the mean is higher. Okay, so we will be performing a right-tailed test because our alternative hypothesis uses a greater than symbol, and the right tail, or the upper tail, is greater than the mean. It's to the right. Okay, it's on the greater side. Okay, step 2. Assuming the null hypothesis is true, determine the features of the distribution of point estimates using the central limit theorem. So by the central limit theorem, we know the point estimates are, and we have to either decide normally distributed or t-distributed. Well, we're making a hypothesis about the population mean, and the point estimates are the sample means. And the sample means are normally distributed if we know the population standard deviation. But in this case, we don't know the population standard deviation. When we don't know the population standard deviation, we use the sample standard deviation as an estimate, but we have to correct for that loss of accuracy by using a t-distribution instead of a normal distribution. Okay? So now that we know what kind of distribution we are using, we need to find the distribution mean and the distribution standard deviation. Okay? The distribution mean is mu, or mu sub x. Okay, that's the population mean. That's going to be, what we're going to use for that is the hypothesized population mean that we see in our null hypothesis. Okay, so that is what our distribution mean is in this case, so 10.5. That's what we are hypothesizing. So we're assuming that hypothesis, and then we're going to test if it's true. The distribution standard deviation, since we're not told what it is, since we're not told what the population standard deviation is, we're going to use the sample standard deviation as an estimate and divide by the square root of n. Okay, so we're going to have to actually calculate this. We'll have to calculate this. We don't already know it. Okay, so as a reminder, sample standard deviation can be calculated as, so we start with x minus x bar, where x bar is the sample mean, squared. We add all that up, divide by n minus 1, and then take the square root of all of it. Okay, so that's what we're going to do. Notice that means we're going to have to first find the sample mean before we find the sample standard deviation. Okay, so let's go. So let's grab our data. Let's throw it in a list here. Okay, so we got our data. So in order to find our sample standard deviation, we first need to find our sample mean. I'm going to make sure I have how much data we have. Okay, you could also go back here. It tells you that in this case we have 22. And then the mean is all those data points added up divided by how many there are. So let's print that out. Okay, so that is our sample mean. But remember, we're looking for the distribution standard deviation. So we kind of have this multi-step thing going on. We first find our sample mean x bar, and then we're going to have to find our sample standard deviation s, and then using that, we find what we're actually looking for, the distribution standard deviation. Okay? So we've done the first one. Now let's use this formula to calculate the second one, the sample standard deviation. Okay, so I'm going to take, let's start with x minus x bar squared, and then I add all that up. Divide all that by n minus 1, and then take the square root of everything. Okay, so that's our sample standard deviation. One more step to go. Now we have to use that to find our distribution standard deviation with this formula here. Okay, so we're just going to divide by the square root of n. So our sigma sub x bar, what we're actually trying to find, is going to be s divided by the square root of n. Let's write it one more time so we'll actually see what it says. Okay, that is what we're looking for. That is the standard deviation of our distribution of sample means. Okay, so step 2 is done. On to step 3. We need to find the p-value of the point estimate. Okay, so since we are estimating the population mean, mu, our estimate, our point estimate for that is x bar. And since it's a right-tailed test, we want to know what's the probability that we're closer to the right tail, or at least as close to the right tail as our actual sample mean. Okay. Now our sample mean, we actually had to calculate it already. It's at x bar, right? So we already calculated it. It's right here. So let's copy that. And so we're trying to find the probability that if we took a sample and this was the actual hypothesis, or this was the actual population mean, then we're trying to find the probability that our sample mean would be greater than or equal to, or more in the direction of the right tail than the sample mean we actually found. Okay. So now we need to convert it to a distribution we can work with. Since we're dealing with a t-distribution, we want to find the t-score. The inequality symbol stays the same. And so we just need to find the t-score. Which is t equals, so that's going to be our point estimate, x bar, minus the distribution mean over the distribution standard deviation. Remember, this guy is the same as our hypothesized population mean. And we found all these pieces. So we are ready to go with that t-score. Okay? So our t-score, let's go down here. Our t-score is our point estimate we found, x bar, minus our population mean, mu. And I haven't used that yet, so let me store that real quick. So our hypothesized population mean is 10.5, so that's what we're going to use. Divided by our distribution standard deviation, which is sigma x bar, which I found right here. So let's print that out. Okay, there is our t-score. Okay, so now that we have our t-score, let's find out what the probability that our t-score is bigger than this t-value, that a sample mean would be bigger than the sample mean we actually got. Let's find that probability. Okay, so since we're dealing with a t-distribution, we're going to use the PT function. Probability of a t-distribution. Plug in our t-score. We need to specify the degrees of freedom, right? It's going to be 1 less than our sample size. So in this case, remember our sample size was 22. So our degrees of freedom in this case is 21. Since I already have n storing the size of my sample, I just need to subtract 1 from that. And then lower tail, since this is a right tail test or an upper tail test, since our inequality symbol here is greater than or equal to, we do not want the lower tail. We want the upper tail, which is in the greater part of the t-distribution. So lower tail, false. And there's our probability. Notice it's very small, right? 0.0002. I mean, it's really, really small. Okay, that is our p-value. Let's paste it in there. Okay, it is our p-value in this case. We're not doing a two-tail test, we're just doing a right tail test. So we only need the probability we're in that one tail. That would be our p-value. Okay, so now that we have our p-value, we can make a conclusion. We can state our conclusion. So our p-value is 0.0002, and we want to compare that to our alpha. So going back over here, we are performing this hypothesis test using an 8% level of significance. That's our alpha. So 0.08. And as you can see, our p-value here is a lot smaller than our alpha. So we are going to reject the null hypothesis. Our probability that we get a sample mean as extreme as the one we did is so small that we are comfortable rejecting the null hypothesis. It is past our threshold alpha. Okay? So now let's interpret that conclusion in the context of the problem. So since we're rejecting the null hypothesis, that means we are concluding that the current average time that teenagers spend on the phone isn't equal to 10.5. We're hypothesizing that the current average is greater than 10.5. Okay, so we conclude that teenagers spend more than an average of 10.5 hours per week on the phone. We want the second option. Submit, and we have it.